Calculations involving titrations is kind of the classic beginning of using molarity calculations as part of reactions. A titration is used to determine the unknown concentration of an acid or base. So there's actually a number of different types of titrations. We start with looking at acids or bases, but really titrations allow us to determine the unknown concentration of something. So where we start at is by looking or determining the unknown concentration of an acid or a base, but there's a lot of different types of titrations in reality. During a titration, the titrant, so you take something of a known concentration called a titrant and you react it with something that has an unknown concentration called the analyte. And typically you do this using a burette. And a burette is just a way of accurately adding a known volume of a solution. And it's this interaction between our titrant and our analyte allows us to calculate this unknown concentration. During a titration, what you're looking for is the equivalence point. And what that is the exact amount of titrant that completes a specific reaction with an analyte according to a balanced chemical equation. So during a titration, there is going to be a reaction that you are following, and really what the equivalence point means is that you've completed a specific reaction. So you've added enough titrant to completely react with your analyte based off whatever reaction you're looking at. Here we're going to be looking at acid-base reactions like we talked about earlier in this chapter, and the endpoint is going to involve when all the acid and base have interacted with each other. Typically, the equivalence point is determined by the change in color of an indicator. So you're going to add an indicator, and that indicator will tell you when you've reached the equivalence point. Kind of the classic one is called phenolphthalein, and when you're looking at acid bases, the phenolphthalein gets a pale pink color that allows you to know when you've reached the equivalence point of the titration. When you're doing a titration involving the neutralization reaction of an acid and a base interacting with each other, for most of those reactions, the equivalence point, when we reach the equivalence point, really what is happening is that the number of moles of acid is equal to the number of moles of base. So it doesn't matter whether the known amount or the known concentration is an acid or base. We can use one to find information about the other one. So when you reach the equivalence point of an acid-base titration, we can say that the moles of the acid are equal to the moles of the base. And this is what we're going to use to determine an unknown concentration. So here is a very classic example. I have 100 milliliters of NaOH that has an unknown concentration. And so what I want to do is find out what the concentration of that NaOH is. So what I do is I titrate it with HCl of a known concentration. So I have 2.5 molar HCl. I titrate it to the equivalence point, and I know that it took 600 milliliters of this 2.5 molar HCl to reach the equivalence point. And so using this information, we're going to be able to calculate the unknown concentration of our NaOH. So that's what we're looking for. And traditionally, that's what you're looking for in a titration, is the unknown concentration of something. So it's really important that you take a second and look at the reaction that is going on, because sometimes there could be stoichiometry involved, and we'll see that in the next example that we're going to do. So when you do a titration, you always want to have the balanced reaction of what's going on inside of the titration, because that might come into play during your calculations. So we've already looked at that. We've taken NaOH and HCl, so a strong base and a strong acid, and we're interacting with them. We talked about earlier in this chapter how to come up with the balanced chemical equation, and so this is it right here. And what's important is to note that the reaction of NaOH and HCl is 1-to-1. So for every 1 mole of NaOH I use up 1 mole of HCl. And so this is going to be the reaction that we're going to use to find our unknown concentration of NaOH. So the first thing I need to do is figure out how many moles of HCl it took to get to our equivalence point. So to find moles, I take our molarity equation and I set it up to find moles. So remember, molarity times volume in liters equals mole. So we had 2.5 molar HCl. We understand it took 0.6 molars, or 0.6 liters of our 2.5 HCl to reach our endpoint. So when we multiply those two things together, we understand it took 1.5 moles of HCl to reach the endpoint. Then what I want to do is say how many moles of NaOH was inside of there. So during the titration, how many moles of NaOH did we start with? And what we're going to do is say when we are done, the number of moles of acid are equal to the number of moles of base. So we know that these two numbers are going to be equated to each other. So really what we're saying is, using our balanced reaction here, is if I used up 1.5 molar of HCl, how many moles of NaOH did it take to cause that reaction? So I'm going to use the mole ratio from this reaction, and remember it's 1-to-1. So I started with 1.5 molar of HCl. That's how much it took of our known acid to reach the equivalence point. And this equation says that for every 1 mole of HCl I use up, I also use up 1 mole of NaOH. So if I used up 1.5 molar of HCl, there must have been 1.5 molar of NaOH inside of the flask. So we still haven't figured out the concentration. All we've done is figured out how many moles of NaOH was inside of our flask, because they're equated to each other because we reached the end point. So we wanted to calculate the number of moles of NaOH that were inside of there, and we did that by doing a titration. So remember that we are not looking for the number of moles, we're looking for the concentration. And so this is kind of a tricky point here. We want to find the molarity of NaOH. Molarity is equal to mole divided by volume. So it is the number of moles of NaOH that were in our starting sample divided by the volume of the solution in our starting sample. And so during this titration, what we figured out is that initially there was 1.5 mole of NaOH inside of our solution, and what we needed to find now is the volume of that solution. And this is very important, a very, very common mistake during titrations, and is to be confused with what we mean by the solution here. So it's a very common mistake. When we say V solution, we're talking about the volume of the NaOH that we started with, which was 100 milliliters. When we look at the original question, we said, what's the concentration of this of NaOH here? And the idea is we started with 100 milliliters. It's very common to try to add on this extra volume that we added during the titration. We're not interested in that. We're interested in what's going on with the initial sample. The initial sample of NaOH was 100 milliliters. So that 100 milliliters is going to show up here in our final concentration for the molarity of NaOH. So we did a titration. We looked at how much HCl it took to reach the endpoint. So we figured out that was 1.5 moles of HCl. From that, we were able to determine that there was 1.5 moles of NaOH in our original sample. And now we understand that the volume that we're talking about is the volume of that initial sample. So we take our 1.5 moles, and remember, always we convert milliliters to liters. So 100 milliliters is 0.1 liters, and we get the unknown concentration of NaOH, which is 15 molar. So don't fall for this. It's very common to try to involve the concentration of that's added during the titration. You don't do that. Really what we're looking at is what's going on with the initial sample. And to gain information about that initial sample, we had to do a titration. In this case, we added 600 milliliters of HCl. So this was used, the 600 milliliters of HCl was used for a different part of the calculation. Is this, you have to remember this volume of solution is the initial volume of the initial sample that we were playing around with. So here we'll do one more example of this idea, but in this case we're going to use a reaction where the mole ratio isn't 1-to-1. And so this is why it's always important to do the mole conversion during these reactions and like limiting reactant calculations, is because sometimes the mole ratio isn't always 1-to-1. And this comes from the idea that some acids have more than one H plus that they can give up during a neutralization reaction, and some bases have more than one OH minus that they can give up during a neutralization reaction. So we always want to take a step and look at the reaction that's going on in our titration and use mole ratios during these calculations. So here we're starting with 100 milliliters of an unknown concentration of sulfuric acid, H2SO4. To figure out what this concentration is, we titrate to the equivalence point with 50 milliliters of 1.5 molar NaOH. So as always during this titration, we want to find out what this unknown molarity is of our sulfuric acid. The first thing I do is figure out what reaction is going on. And so we talked about that earlier in this chapter. H2SO4 is a strong acid, NaOH is a strong base. We do the reaction, so we interchange the ions and balance it. And so this is the overall reaction that's going on here. The difference that we have with this problem that we didn't have in the first one is that the mole ratio is different. So for every 1 mole of H2SO4 we use up, we also use up 2 moles of NaOH. And so this is going to have an effect on our calculation. So the first step here is to find out how many moles of NaOH it took to reach our endpoint. And so once again, that is molarity times volume. So the molarity of NaOH times the volume of NaOH that it took to get to our endpoint will tell us how many moles of NaOH that we needed to complete this reaction and get to our endpoint. So we had 1.5 molar NaOH that was given. It took 50 milliliters to get to our endpoint, and so overall we know to get to our endpoint, to complete this reaction, it took 0.075 moles of NaOH. And now what I'm going to do is say, if I used up all of my NaOH, how much sulfuric acid was used up to complete that reaction with our NaOH. So I do a mole conversion using this reaction. I know it took 0.075 moles of NaOH, and then from this reaction I know it's a 2-to-1 mole ratio. So it says for every 2 NaOH I use up 1 H2SO4, or we can say for every 2 moles of NaOH we use up 1 mole of H2SO4. So I do this mole conversion. Remember, the moles of NaOH cancel. That'll give us the mole of H2SO4. So this calculation tells us how many moles of H2SO4 was inside of that original sample. So we get that it was 0.0375 moles of H2SO4. And in the final step, remember, we're not interested in moles, we're interested in concentration. To find the molarity, it's mole divided by volume. We know how many moles of sulfuric acid were inside of our initial sample. We then divide that by the volume of our initial sample, and once again, remember, it's not we're not involving the amount of or volume of NaOH that we use to do the titration. We say of that initial sample that we had, that was 100 milliliters or 0.1 liters. So remember, we always want to convert from milliliters to liters, and what we end up getting is that our concentration of H2SO4 is 0.375 molar.